The paper finishes with question 6, which is a fairly comprehensive question on differential calculus. You are given this container here, and in part A, you're asked to write down a formula for A, which is the surface area to be coated. So you can imagine here that if you're taking your cylinder here, in effect, we're going to have the base, so we need to cover the inner surface area. So the first thing we need to do is cover the base, so this area here, and that's just going to be the area of the circle. So we can say that the area equals pi r squared, because we've got r here. In order to calculate the internal surface area, the best way to think about this is that we have got here, this is the top of the container. Now we can work out this circumference of the cylinder here by doing, so we're going to add here 2 pi r. So that 2 pi r represents the top here. Now because we're coating the interior of the whole cylinder, we need to take the circumference and multiply that by h. So this will give us the total internal area. So this part here is the base, so that's just the area of the circle here, and then the second half is kind of the internal walls. So we found the circumference of the top, and we've multiplied that by the height, and that will give us the internal area of the cylinder. In part B, we are asked to, or we're told that the volume of the cylinder equals 0.5 meters cubed, and we're asked to convert that into centimeters cubed. So the way to think about this is, if you imagine, if we take a cube, so here's our cube, and we're going to say this is a meter cubed. So if we have a meter cube, 1, 1, and 1, so that gives you 1 meters cubed. In centimeters, that's going to be 1 meter equals 100 centimeters, that's 100, and that's going to be 100 centimeters. So in centimeters cubed, we're going to do 100 times 100 times 100. So 1 meter cubed is the same as 1,000,000 centimeters cubed. So to get from meters cubed to centimeters cubed, you need to multiply by 1,000,000. So if we here take 0.5 meters cubed and multiply by 1,000,000, we will end up with 500,000 centimeters cubed. In part C, we asked to write down, in terms of R and H, an equation for the volume of this water container. Just remember that whenever you see write down as a command term, it should be fairly straightforward. So here, we should be able to recognise that to find the volume, we're just going to take the base, which is going to be, the volume is going to be the base, which is pi r squared, and we're going to multiply it by the height. So the volume is going to equal pi r squared h. In part D, this is when it starts to get a little bit trickier. We are asked to show that the area equals pi r squared plus 1,000,000 over r. Now, at first glance, that looks a little bit intimidating, but let's try and break it down by using what we already know. So if I draw you back to the first part of the question, we've already said that the area is the same as pi r squared plus 2 pi r h. Now, the problem here is that we've got two variables. We've got r, which we want, but we've also got this h thing here. So what we're going to have to try and do somehow is get from here, we want to eliminate or get rid of the h term so that we have an expression for the area just in terms of r, because that would make any potential differentiation easier. So how do we change this expression here from including the h variable so that it only has r? Well, we know we have already found that the area, that the formula for the volume is pi r squared h, and we know what the volume is. We've been told that the volume is actually equal to 0.5 meters cubed, which we said was 500,000 centimeters cubed. So from here, we're going to substitute in the volume, which we know is 500,000, and we're going to set that equal to pi r squared h. Now what we can do is rearrange this equation to give us a definition for h. So we can rearrange this to say that h is going to equal 500,000 all over pi r squared. So that's what I've done here. Now what we can do is we can take this definition of h and we can substitute it into this equation. So we're going to say here that the area equals pi r squared, that bit doesn't change, plus 2 times pi times r times 500,000 over pi r squared. Now, hopefully what you can see here is that that pi is going to cancel out with that pi, that r is going to cancel out with the r squared term here, and I am going to be left with pi r squared plus 2 times 500,000, which is 1,000,000, all over r. Now, what you might like to do as well, bearing in mind we're probably going to be looking at differentiation, is just rewrite that as pi r squared plus 1,000,000 r to the minus 1. But you don't actually need to do that last step because you're asked to show that the area equals pi r squared plus 1,000,000 over r. So this is the answer, but just with an eye to what's coming on next, this might be useful. Part E asks us to differentiate the area with respect to r, and it asks us to do that by asking us to find dA by dr. So here it's just going to be straightforward differentiation in the first part. So if we differentiate the first part here, if we bring the exponent down, it's going to be 2 times pi times r to the power 2 minus 1, which is just 1. Now, the problem with the second part is that you've got r to the power negative 1. Now, very often people here will say, bring the negative number down and then subtract 1 from this and end up with 0 and just say that it's a constant term. However, you need to remember that, yes, we are going to take the negative down, so it's going to become negative 1,000,000. And then if we've got negative 1 and we subtract 1, that's actually going to be negative 2. So we can rewrite this as 2 pi r minus 1,000,000 over r squared. Again, these last two things are equivalent. You don't need to do this, but it's just a bit neater. In part F, we are asked to use your answer to part E to find the value of r which minimizes the area. So the key thing to recognize here is that at a minimum value, the gradient, or the rate of change of area with respect to the radius, will be equal to 0. So we've got at the minimum value, dA by dr is equal to 0. So if you think about it on a graph, if we have a minimum point here, at this point here, the gradient, or the rate of change here with respect to area with respect to r would be 0, so it's a flat line. So that's how we can identify the minimum point. So if we set the derivative dA by dr equal to 0, we can actually solve it. So this is our derivative here, so we can actually set that to equal to 0. So we'll say 0 equals 2 pi r minus 1,000,000 over r squared. So we can then rearrange that and say 2 pi r equals 1,000,000 over r squared. So we can say that that is the same as r cubed equals 1,000,000 over 2 pi. So we end up with r is equal to the cubed root of, that's going to be, just simplifying it, 500,000 over pi. And that gives us 54.2 centimetres to the nearest 3 significant figures. In part G, we are asked to find the value of this minimum area. So we found that the value of the radius which minimizes the area was equal to 54.2 centimeters. So in order to find out the minimum area, all we're going to do then is substitute this value of r into the equation for the area. So we're going to say that the area equals pi times 54.2 squared plus 1 million divided by 54.2. And if you do that, you end up with an answer of 27,679 centimeters squared. The final part of the question, question 8, tells us that 1 can of water-resistant material creates a surface area of 2,000 centimeters squared, and asks us to find the least number of cans of water-resistant material that will create the area in part G. So we're going to take our area, 27,679, we're going to divide it by 2,000, and that's going to give us 13.84. So in order to completely cover the total area, bearing in mind we can only buy complete numbers of cans, we will need to buy 14 cans of water-resistant material.